No. Okay, so what did we do last time? We reviewed the FRW universe that we're studying particles in. We talked about the thermodynamics of gases of particles in FRW, especially equilibrium thermodynamics. Thermal relic dark matter is entirely a question of analyzing things that are in equilibrium, out of equilibrium, and the process of moving between those. So that's why equilibrium is important. And then we started talking about the WIMP, and let me just remind you kind of quickly. And really, I mean more generally, so 2 to 2 dark matter whose relic density comes from 2 to 2 annihilations. So this is the dark matter. This is something that it's annihilating to. These start faster than Hubble, and then they freeze out at the moment where the number density times the cross section is Hubble. And then I told you the sort of back of the envelope way of estimating the relic density. Okay, so the relic density, which should be order 1, is the mass times the yield over T equality, sort of up to order 1 number. This is just number density for entropy. And then you just solve this equation for n, plug it in. And then if you just estimate, entropy goes as T cubed, Hubble goes as T squared over on Planck. This happens for temperature near the dark matter mass. Then you arrive at a simple expression where the only scales are the temperature of matter, radiation equality. And the Planck scale, this comes from how much dark matter we measure. It's 1 eV. This comes from the Hubble rate, 10 to the 19 GeV. And therefore, for this to be order 1, the cross section should go like 1 over T equality and Planck. This is an energy scale of about 100 TeV. But if you estimate in some actual model of WIMPs, this would be, say, some alpha weak squared over m squared, where this is some couplings. And then if you solve for m, you get alpha weak, geometric mean, T equality, and Planck. And this turns out to be near the TeV scale, which is an interesting scale in particle physics. Okay, so that was what we did last time. Any questions about that? Okay, but really this sudden freeze out is an estimate. The more precise way of doing things is to solve a Boltzmann equation for the number densities. And then this estimate is an estimate of the solution of that. So let me describe the kind of more technically correct way of doing this. So, Boltzmann equation. Okay, and I'll just recommend a really great reference for learning about this carefully. It's a classic paper by Gonzalo pre-archive 91. So I really recommend that. Okay. Now, before I write the Boltzmann equation, let's just consider an inert particle that is experiencing no interactions. Then its number density only changes with the expansion of the universe, or its number density in a co-moving volume is constant. What does that mean? That means that the number density times a co-moving volume, which is proportional to the scale factor cube. We take the time derivative, that is 0. So that this would be, this is an inert, sorry, inert particle. So by inert, I mean particle experiencing no interaction, something like this is not happening, then the number density in a co-moving volume is constant. Now, if I divide this by a cubed, then I can rewrite this as m dot plus bh m. So the time derivative of the number density plus this term is 0 if nothing is happening. So that this term just encodes the dilution from the expansion of the universe, and the Boltzmann equation is going to be basically, if you now are not inert and you have interactions, then the 0 is replaced with something that encodes the interactions. So, and I should say, if you're kind of being careful, then technically you can write down a Boltzmann equation that describes the evolution of the phase space distribution, the full phase space distribution. And this I might call an unintegrated Boltzmann equation. It's in the notes, but I'm not going to write it on the board now. But if here we're assuming you're in kinetic equilibrium, and then the phase space distribution is the equilibrium phase space distribution, and there's only one unknown, which is the chemical potential or the total number density. You can trade those. So I'm going to write, when I say Boltzmann equation in these lectures, I'm going to mainly be talking about a Boltzmann equation for the total number density, which you could call an integrated Boltzmann equation. So that's a sort of technical aside for the experts. Okay, but anyway, so this is going to equal something. That would be 0 if there were no cross section. And in the case of this 2-to-2 annihilation, there'll be 2 terms. The term that encodes the annihilations. So it's a minus sign because you're removing dark matter. And then a term that encodes the opposite process of creation of dark matter from these bath particles phi. Okay. So if it were inert, then the cross section would go to 0, and this would go to 0, and we go back to this limit. But when this cross section is present, then this is what encodes the interactions. Okay, and this can be simplified. A really useful trick when dealing with thermally average cross sections. Yeah, sorry. By this I mean, let me label this by the initial state. So this I mean the thermally average cross section of chi, and then this is thermally average cross section of the inverse process. So here my label is describing what's in the initial state. Okay. Now detailed balance is a very powerful idea that allows us to relate forward and backward processes. It tells us that in equilibrium, forward and backward processes balance. Or in equilibrium, the right-hand side of this equation would be 0. And that will allow us to simplify this. So here, here I meant the number density in general. If I write EQ, then I mean the equilibrium number density that we wrote down last lecture, assuming 0 chemical potential. So detailed balance relates the 2 cross sections as follows. So thermal averages respect this property that the right-hand side vanishes if the 2 distributions take their equilibrium values. And the reason this is a useful simplification is it lets us remove this term, and then we can write this equation just in terms of one cross section for the forward rate, and then we don't have to separately write it the backward rate. Yes.
So this is only valid when we're in equilibrium.
Yeah, it's valid. Well, this equation is valid always, but it's the equilibrium number density that appears in front. But this equation tells you about the form of these thermal averages.
But why would this equation be valid always? I mean, I would think that if these two numbers are equal, then the only thing that dilutes my chi is the expansion due to Hubble. So
No, because they'll in general have different masses, so the equilibrium distribution will exponentially suppress the heavier thing. So even though forward and backward rates balance, the number densities are actually not equal. They're just driven to equilibrium.
okay.
Yeah, which is just to say that the solution to this equation will want to set the right-hand side to 0 when the rates are fast. Okay, so you can solve this for this and plug into here, and then we arrive at a simpler equation. And also, I'm going to now assume, so far I've written the general fine number density, but for WIMPs, we assume that you're annihilating into something in equilibrium. So I'm going to assume this. This will be certainly true if you're annihilating into standard model particles. More generally, it's actually not always true, but it's an assumption for this WIMP freeze-up story. So if I assume this, then I can put equilibrium here, and then I can solve this. Then I arrive at the following equation. Yes.
I'm a little bit confused about that assumption. So the standard model particles are in equilibrium, but their number density is changing because of these interactions with pi.
Well, sorry, the standard model particles are going to, at high temperatures, so say above an MeV, they'll all be in equilibrium with zero chemical potential. So their number densities are just given by the equilibrium equation. The interaction with dark matter doesn't affect that. That's true whether or not it's interacting with dark matter. It's a consequence just of the standard model interactions. So and then adding the dark matter allows the dark matter to also be in chemical equilibrium until it departs, and then that's what this equation describes.
Okay, thanks.
Okay, so now all you need to do is plug this, type this in a computer and solve it, and then you're done. And then the form of the solution will, it turns out, be replicated by the sort of simple estimate we did to within a factor of 2, say. But you'll get some, if you're plotting yield versus x, you'll get some curve like that. Solving it carefully will let you describe the sort of shape of this as it departs, but it will be given by the sort of intuition that I gave you by just saying falling exponentially and then constant. Let me just so you definitely need a computer if you want to describe that point shape carefully, but we can kind of inspect this and figure out the behavior in the sort of extreme limits of high or low temperature. So let's consider the case where you're either very in equilibrium or very out of equilibrium. So in the limit, sort of initially, the rate is going to be much faster than Hubble when the number density is still large. So when the temperature is on the order of m chi. And then this will just want to set the right-hand side to 0, and therefore the solution will be that m chi is approximately given by the equilibrium value. And then in the opposite regime, where it's much slower than Hubble, then we can neglect the right-hand side, and then you're just driven by the Hubble expansion, like an inert particle. And then that will just mean you have constant yield. So now y pi per entropy is going to go to some constant value. And then you want to choose the value of the cross-section such that this constant value is the amount we observe. Okay. And I sort of argued last time that the energy density is proportional to mass times number density, and then this T equality sort of gives you the order 1 number. But if you want to get the factors of 2 right, let me tell you the more careful way of doing things. Here I'll include the H squared. And this sort of 1 over T equality factor you can write in terms of quantities today. So this is the entropy of the universe today. And then the critical density today. So that's the sort of careful prefactor. And this we observe 0.12. And then if you now solve this, if you plug in again, so let's see, this value I gave you last time, it was 10 to the minus 5 GeV per centimeter cubed. The entropy today is 2900 centimeter cubed. I'm plugging that in, getting your units right. You'll find that the correct observed energy density is reproduced if mass times yield is about 0.44 electron volts. Now, right, the yield is dimensionless, right? Remember, it's number density for entropy. So if the mass is far heavier than an electron volt, like for a weight model, the mass would be weak scale. That's telling you the yield is very small, and that's telling you that, and then because the entropy is going to be similar to the photon number up to an order 1 number, it's telling you that the number of dark matter per photon is a very small number, 10 to minus 10 or something. Yeah.
So you assume that the number density of the pi particle is constant and equal to the equilibrium number density?
it's never constant.
Here,
But sorry, assume
the at the bottom there. No, wait.
here.
To the left. Below the detail balance.
Oh, sorry, phi. Yeah,
Fine, yes.
yes.
So.
Yes.
So you assume that it's constant regardless that the dark matter particle annihilate into phi?
Yeah, this is not a constant. It's the equilibrium distributions that we discussed last time. So it would go like t cubed or e to the minus m over t. Yeah, typically it would be, say, much lighter. So this would typically be scaling like t cubed, but it would be given by the equilibrium distributions from last. Okay. So now that we're doing the order one numbers correctly, if you ask what should this be, our sort of back of the envelope estimate was 1 over t equality on Planck. The precise value ends up being about 1 over 20 TV squared. And within, this will always be correct within a factor of 2, sort of depending on the detailed shape of this curve. And this, well, it's popular to quote this in more even units for some reason. This is minus 26 centimeter cubed per second. But our sort of very crude back of the envelope got the scale right to within a factor of 5 in scale in this case. Okay. Yes.
It's a very basic question, but I don't understand like why you compare this n times sigma b to the Hubble constant. Why
Oh.
is the comparison?
Well, yeah, just because I'm comparing the size of different terms in the Boltzmann equation. So there's always sorry, these are always n chi's. Mixed notation here. So there's here you have h times n, and here you have sigma times n squared. So if I want to say, is this term bigger or is this term bigger,
I see.
then it's equivalent. I divided by an n, and it's equivalent to this, and that was just this is the rate versus Hubble, so it's just the rate comparison. And the freeze out is when they're equal. So here I'm comparing the two regimes, either far from freeze out or one rate is much bigger than the other. Yeah.
Could you repeat the argument, please, about the relationship between the photon density and dark matter density? I didn't quite.
Oh, yeah, sorry. So m times y is 0.44 eV. Now, y is n chi per entropy. Okay, and then entropy goes as t cubed times order 1 numbers like g stars, and also the number of photons goes like t cubed times other order 1 numbers. So the number of photons and the entropy are the same of the order 1 numbers. So if the mass of the dark matter is far heavier than an electron volt, like in WIMP models, then that tells you this y is a small number, which tells you that the number of dark matter is very small compared to the number of photons. By sort of the ratio of EV and dark matter mass, which if you're a TeV is a lot, 10 to the minus 12. But and the way you can get such a small ratio is from the exponential in the Boltzmann. So you very quickly have a very small amount of dark matter once you start falling down this exponential. Okay. Any?
One more question.
Yeah, please.
What is measurable? Is a y measurable or is any of this measurable?
The energy density today is measurable, or omega. This is what we measure, say, right? Which is defined to be the energy density of dark matter today over the critical density.
Okay. Everything else you derive from this measurement. Or you can't derive. Okay.
Yeah, one number is measured the amount of dark matter today, or really more precisely, it's a lambda CDM fit, and the most precise information is really from the epoch of recombination. But then they'll report it in terms of the energy density today.
Okay.
And then after the freeze out, nothing is happening to the dark matter. It's just a dilute gas of non-interacting particles. So you can take what you see today, and then just given the redshift, you can extrapolate that back to the freeze out moment. And then that tells us how much we need. That's that for all of my lectures, that's the only measure.
Okay.
So we're just aiming at ways of producing the amount of energy density of dark matter we see today.
Okay.
Okay. Any other questions? Okay. So that is the WIMP, and now we will go beyond the WIMP. And the WIMP is really an example of a much broader set of ideas. So what I want to do now is sort of generalize, or kind of give you a sense of how broadly the story we just described applies, and then give other examples. This will be within the domain of thermal relics. Yeah, typically symmetric. Thermal relics for the WIMP is like the prototypical example. Okay, so there's a couple of assumptions that define a symmetric thermal relic. And these assumptions I may have mentioned, but they're kind of implicit in my discussion of the WIMP. So now let's just make it very explicit. It's all did sort of come up. Okay, so number one, we assume kinetic equilibrium throughout the dark matter production. And with this, remember, kinetic equilibrium means rapid energy transfer, which pegs things to the equilibrium the distributions. And that could come about, well, for example, from dark matter scattering against bath particles, which could be standard model particles. It could be literally scattering against the thing that it annihilates to. So you could rotate the annihilation diagram. That would be an example of a diagram that could maintain kinetic equilibrium, and then many other processes that could too. And as long as this exchanges energy much faster than Hubble, then that will ensure that there's a temperature and a notion of a equilibrium phase-space distribution. So this will lead to there being a temperature of the dark matter. And in general, that temperature may or may not be related to temperatures of standard model particles, but for this lecture, I'm going to furthermore assume that this is the photon temperature, and then this afternoon we'll relax that assumption and consider cases where it's not. Okay. And this we're going to assume to hold throughout the production. So you're going to be in kinetic equilibrium, and then you'll be looking at the departure of chemical equilibrium. Okay, so number two, we assume initially there are processes that rapidly deplete high number, which for the WIMP was annihilations, but there are many other possible processes that could achieve that. And so technically, we're assuming that some processes are setting the chemical potential of the dark matter to be zero initially. So sort of when, say, the temperature is on the order of the dark matter mass. And then when the temperature drops below the dark matter mass, in the WIMP case, we saw that you go through this freeze out, but initially you begin in chemical equilibrium. Number three was an assumption that I didn't mention before, but I was implicitly making, which is that there's no asymmetry in the dark matter. In general, the dark matter may be its own antiparticle, or there may be a dark matter and anti-dark matter. So those are both viable possibilities a priori. And I'm assuming here, that's why I used the word symmetric, symmetry, which means, well, this can be achieved in two ways. So sort of option A would be the dark matter is its own antiparticle, and then I can't have an asymmetry, like if it's a May or non fermion. Option for a real scalar. Option B would be if the particle and antiparticle are distinct particles, then I'm assuming that they have the same number density. If that doesn't hold, then you need to track the size of the asymmetry, and in general, the energy density could be like baryons, where there is an asymmetry, and that leads to the amount of baryons we see. Yeah.
Are you also assuming there's only one type of dark matter particle, or could there be multiple?
Yeah. So there can always be multiple. So sort of any of the ways I discussed in these lectures for producing dark matter can be applied to the multiple case. the only case, the place where that assumption entered in the prior discussion was when I set, say, my equals T equality up to order one number, or more precisely, 0.44 eV. So assuming that if there's only one dark matter, this is an equals, and then if you're just making a subset of the dark matter, it's a less than equals. So in the WIMP case, I said cross section equals blah. If it's a subdominant fraction, cross section is greater than blah. So I'm not going to keep stating that assumption because that assumption will underlie everything I say, but I'm just going to aim at all, and then you can, any of these mechanisms you can in general make less. Yeah.
There's a race tag online. Maybe it's Josh who can probably just speak up.
Yeah, you can speak up, but or I can read this.
Yeah,
What
yeah.
initial condition should we input? Ah, yeah, good.
Good question. The equation that I've erased, assume the WIMP Boltzmann equation, the initial condition is equilibrium. So I was assuming at high temperature, the dark matter begins with the equilibrium number density, and then the equation will describe the departure from that. Yes.
But do we know that initial equilibrium density, and couldn't it have been anything?
It will if you make assumptions 1 and 2, then yes, and it's given by the equilibrium equation I wrote down. So if dark matter has rapid interactions, it will be in equilibrium, and that's the assumption underlying this thermal relic framework I'm describing. Dark matter might not satisfy that assumption, and then you're in the world of non-thermal dark matter models. Yeah.
So I didn't quite get point 2 of this assumption.
In the case of WIMP, point 2 was that I have rapid annihilations compared to Hubble initially. And now number 2, I'm just generalizing that. There are some processes, which I'm not yet specifying, that rapidly deplete or that rapidly change dark matter number density, and that allows you to enforce chemical equilibrium initially. But it doesn't need to be this, it can be something else.
Why can't we assume that physical potential is 0?
Generally, you can't assume it, so I'm assuming it. This interaction would do that if state phi has no chemical potential, and if this is faster than Hubble, then it sets this chemical potential to 0. So by number 2, I mean something like this is happening, but maybe it's not exactly this process. And I'm going to show examples in the rest of the lecture where the process achieving number 2 is different. Okay. Any?
Josh.
I just hate to belabor the point. On this initial condition, how things start out, are we relating the initial conditions of the dark matter number density to our phi number density? Because I know how many standard model particles I should expect. Is that how it's going?
Yeah, if it's in equilibrium with the standard model, then it has a standard model temperature.
Okay.
Yeah, I mean the beautiful and also unfortunate thing about equilibrium is it washes out initial conditions, in the sense the equilibrium. If you're in equilibrium at some moment, then you lose any information about what occurred earlier. So if dark matter has rapid interactions with the standard model bath, then it's going to be in equilibrium at some moment where they're rapid, and then you're actually insensitive to what happens earlier.
So we can't exactly put a number on it, but I know that these two number densities are in equilibrium.
We can put a number on it. If you know the temperature, then it's given by the equilibrium number densities from last lecture.
Okay.
Like if it's relativistic, then n goes as t cubed.
Sure. Okay.
Okay. Would somebody online like to use audio?
It's Josh. I don't know if we hear him.
Yes. Hi. Can you hear me?
Yeah.
Yes.
Yes, we hear you.
Okay. Yeah. So my question is, so we've been talking about, so we need a kinetic equilibrium, for this picture to be valid. So you have to have like some kind of interaction with, so dark matter has to have like some kind of interaction with some other particles. So, and, there are also, strong constraints on, the dark matter baryon cross sections. So does that have any implications on these kinds of models where you have a WIMP miracle,
Yeah, that's a good question. And the answer is yes, it has implication. And in general, you can, in a large amount of parameter space, have kinetic equilibrium at early times and still be consistent with bounds today. But there are also cases where you would have excluded it. Direct detection experiments have excluded a lot of the a priori WIMP parameter space from a few decades ago. So it's interesting, and it depends a lot on the details. So you really need to look at a specific model, look at the form of the interactions, and then other lectures will talk a lot about those constraints. And then you have to try to remember these lectures and try to connect it. And those connections are interesting and what people write papers about.
Okay.
But the easy way out is if it's just a non-standard model state encoding things, and then my whole story here applies, and then there's no bound, but that's also less interesting. But in general, yes, you can maintain, you can satisfy assumptions 1 and 2 with interactions with the standard model evading current bounds, but it's not obvious a priori, and some of the parameter space that satisfies 1 and 2 is inconsistent with experiments.
Okay, yeah.
Okay, anybody else? Okay. And I want to emphasize the universality of this. So again, WIMP was just one example, but this applies much more broadly. And for any model that satisfies 1 through 3, the same plot I drew before will apply. Where we have number density per entropy and inverse temperature, and you begin in equilibrium and freeze out. So initially, you go to minus x. I'll call this moment x freeze out, and then you have the value that we see today. So this plot that I drew for the WIMP, it applies in general to thermorelics. And that means that there's a universality in terms of what the freeze out temperature should be simply to match observation. So you could ask, what is this? And let me do it carefully this time. I'll keep the order 1 numbers. Okay, so matching the abundance, we use the careful version of the prefactor. And here I'm going to sort of use the sudden freeze out approximation, like that, that at this moment, the value is the final value. Of course, in reality, you need to solve a Boltzmann equation and to get the sort of factors of 2, you want to get the shape of this curve and so on. But in the sudden freeze out approximation, you just assume that you go directly from equilibrium to constant, and that will be okay to the factors of 2. Okay. So freeze out over entropy of freeze out, it should equal 2. So I gave you the form of equilibrium number density last time. I'll just remind you, and this time I'll write it in terms of this x parameter. If you remember this, last time I wrote it in terms of m and t, but now I'm going to trade t for x. Okay, so that's the dark matter number density of freeze out. The entropy of freeze out is the following. Right, so this was e to the minus m over t. This was t cubed. I've rewritten that in terms of x, for x is m over t. And then you can just plug these into here and solve for what x should be. If I do that, I find 28 plus log this is the number of degrees of freedom of the dark matter. I'll just normalize it to 2 for the hell of it. I'll take g star s to normalize to 100. So it's given by this plus terms that are slowly varying that are order log of log. The reason for this is if I plug these in and then take a logarithm, then I remove this exponential. I have logs of the other order one numbers, but I also have logs of x. So I have an equation where it's x equals stuff plus log of x. So that you can solve numerically, but it gives corrections that are order log if you ignore the log of x depends. So that's the reason for this. Okay, and now this will vary, say, between about 10 to 30 if I take this mass to be over a wide range, say maybe to 100 TeV or so. And this will apply to any thermal relic, and here I'm just using the assumption that it is in equilibrium, and then the parts equilibrium has a constant value. If we demand that constant value matches observation, then the freeze out has to occur at the right moment. And then it's just a matter of choosing interactions that satisfy assumption 2, and then depart at this moment that matches observation. Okay. Any questions? And so this is all, everything here applied to the WIMP. But now for the rest of the lecture, I want to give other examples of models where the interactions that satisfy number 2 are different from annihilations. And that'll give you an idea of more how broadly this paradigm applies. Okay. Any questions? Okay. Yeah, and looking at more examples will give us at least some practice thinking about Boltzmann equations in a quick way. So everything I'll discuss now will also involve a 2-to-2 process, and then we'll generalize that later. Post 2-to-2 zoology. And let me now just introduce the different animals, and then we'll talk about each one. Okay, what we've talked about so far is Pi, in so-called WIMP like, where the like is because this might not really be the weak interactions, and then as I'll describe the mass scale, it can be different. Now, an implicit assumption here that I'm making so far is actually that M-Pi is heavier than M-Phi. So a variant of this is called forbidden. It's the same process. So now you reverse the assumption, you're actually now letting something heavier. Okay, and then another option. Here you have 2 dark matter in the initial state and 0 in the final state. But you could have a dark matter in the final state. This still allows you to change the dark matter number density, so this is fine for establishing chemical equilibrium. This has been named semi-annihilations. Okay, another variation is to have multiple sort of dark matter species that can appear in the initial state that mutually annihilate. And this is called co-annihilations. Another case is actually, so far it's always 2 dark matter particles in the initial state, or there's an index on them. But you could have just 1 in the initial state and scatter against the back particle, as long as you are transformed into some other particle that is not the dark matter. So this is called scattering. Okay, so I'm going to now explain each of these in turn, but I just want to give you a preview of and these are all symmetric thermal relics where the assumptions and the cartoon that I drew are going to apply to all of these examples. Okay, yes.
Sorry, the forbidden one, is it really depleting the wind density?
But it is, the annihilation is still happening, but just to something heavier. And as long as this has zero chemical potential, so this has to have its own rapid interactions to enforce that, but then it still works. And I'll talk more about it. So maybe hold off on questions. Yeah.
Because about the same thing, so I'll.
Okay. Yeah. I think, yeah.
Also, for things on the semi-annihilation,
Mhm.
is it okay in the QFT sense? Because are you like violating some quantum number?
I never violate rules. This is okay. In fact, I'm going to talk about the symmetries here. That's a good question. Because these four are all consistent with the Z2 and this isn't. But this can be consistent with the Z3. So it will have a different symmetry structure. So, okay. So any other questions? Okay. Yeah, this shouldn't make sense yet because I'm gonna talk about each of these. So first, let's talk about WIMP life, which is what we've already been discussing. I'll just mention the sort of standard WIMP would be weak interactions. And then there was sort of an alpha weak that appeared in my estimate, if you remember. I said cross section goes like alpha weak squared over mass squared. But so by WIMP like, I mean, if you kind of generalize that to consider now some arbitrary processes, the coupling strengths could not be determined by standard model parameters. They could be very different from standard model size. So this would sort of be in the framework of, say, a dark sector that the dark matter lives in. So here you have the standard model gauge group, the standard model particles. There could be a dark gauge group, dark particles. There might be a coupling between them. And then it could be now in this sort of framework, the state phi that appears in these various things could be a dark particle and not a standard model particle. So this sort of dark sector paradigm is something people really have in mind now for sort of any of these different types of thermal relics. It could always be happening in a dark sector. And just as a concrete example, if we take, there would be a dark photon. So there's a U1 gauge group in here that's distinct from our photon. Then we could contemplate dark matter annihilating into dark photons. We'll go down to D here. So here, say dark matter could be like a dark electron, and this could be just a dark QED, and then annihilates into dark photons. That there could be some interaction that keeps this at the same temperature as our sector. But now in the actual annihilation that removes the dark matter here it doesn't involve standard model particles at all. And that means the coupling strength here is a priori undetermined, and also the masses of these particles is a priori undetermined. Here, if you compute the thermally average cross section, you find it goes like an alpha dark over n pi squared, where that's the usual G dark squared over 4 pi. This is the dark gauge coupling, and the dark gauge coupling could be anything. It's technically natural for a gauge coupling to be a very small parameter, even though in the standard model we observe them to all be percentage or bigger. But there's nothing wrong with the gauge coupling strength of 10 to the minus 10. Yeah.
Is there any reason to think that the symmetry groups describing the dark sector would be the same as the symmetry groups describing standard model?
Could be, or could be totally different. But yeah, I mean, there are models of mirror sectors that these appear in solutions to hierarchy problem in the context of something called twin Higgs, where you have a Z2 that replicates the standard model or pieces of the standard model. But you could also just have something totally different in general. So you should be open-minded. So now the whole WIMP story that I gave applies exactly to this type of model with no changes. It's just that now this needs to be given by this sort of 1 over T equality on Planck scale that we estimated, or more precisely 1 over 20 TeV squared. And now if you solve for m pi, you have alpha dark for T equality and Planck. If alpha dark is the size of alpha weak, the weak interaction alphas, then this would point to a mass scale to TeV. But in general, it's different. So I can write this like this. Now, if I allow for alpha dark to be much smaller than alpha weak, I can have a mass scale far below the weak scale, and that would still be perfectly fine. And in general, this, as a very alpha D, can really range from, say, KeV to hundreds of TeV. And that whole mass range is allowed if I just vary this alpha D. Here, in principle, it could have even been lower, but in practice, you run into bounds on warm dark matter below here. So this just experimentally, that if it's all the dark matter, it gets truncated here. If it's less than all, it can even go below that. This upper bound just comes from how big can I make alpha D? And alpha D, roughly speaking, needs to be less than about 4 pi. These are called unitarity bounds. And you can analyze this more carefully with partial waves, and this goes back to Bryce, Konikowski. 1989, and this which just corresponds to the case where this hidden sector is strongly coupled. That would give you the largest possible mass, and if it's very weakly coupled, you can get a much smaller mass. In one variation of the case where this is very light is actually by Jonathan Feng, called WIMP-less. I think he will mention it maybe in his lectures too. It's also been called secluded dark matter. But anyway. Okay, so even just this simple WIMP idea that I gave you actually points to a really broad range of masses if you allow the parameters to vary over the full possible range. Yeah.
So you said that the experimental constraints that can't go below KeV, but people consider even lighter dark matter. So how does that play together? I mean,
Yeah, if it's all the dark matter, then if it goes below, if it has a thermal origin like this, then below KeV, it would be too warm, or hot today, and it would mess up large scale structure. The way you can go below KeV, and I'll talk about models like this in the last lecture, are if it's, say, a boson all in with zero momentum, and then like Axion can realize that.
Okay.
And the reason this is not that is because here we're starting in chemical and kinetic equilibrium with an equilibrium phase space that occupies all momentum modes. In order to go below KeV, you cannot have the high momentum modes, and you have to just all be at rest. And there are ways of making dark matter like that, but they're very non-thermal.
Okay.
So sort of within the thermal world, that this is a lower limit. And if it's all the dark matter, if it's less than about 10%, then it's okay again, because the warm limits are really sensitive to the bulk of dark matter. So you could also literally take this model and go below KeV as long as I make it say less, a few percent or less of the dark matter that way.
All right, thanks.
Okay.
I have a general question. So in the thermally average cross section, in some references, people say V is the relative velocity, and some people say the molar velocity.
Yeah, I think the answer is
So,
molar, but the
I think there's a big confusion with this literature.
place
Because
that,
it depends on the paper you read. That is,
yeah, the reference I recommend is the one I gave before, which was Gondola Galmini 91, and they're the ones who have an argument about it being the molar, and but
so it's not only head collisions, it can be all sorts of collisions between.
yeah, I'll write an expression for sigma v explicitly, and you can do it without reference to velocity. So this interesting question conceptually, what velocity appears, but technically you can actually avoid this and just do the thermal average explicitly. But yeah, Gondola Galmini is the place I recommend for this type of deep question. Okay. Any other questions? Otherwise, well, let's talk about this case. And actually, this is one where the thermal average will, doing it correctly is really important. Okay, and this goes back to an awesome paper by Rice and Seckel from 1991, which they call 3 exceptions to the calculation of relative abundances, and they actually are the first to consider both this case and this case. The third exception is they considers poles, where like these two masses are near something that goes on shell. But I'm sort of grouping that in this category in this lecture. But anyway, and they call this a forbidden channel because it's not allowed at 0 temperature. Where at 0 temperature the chi are at rest, and then you cannot make something heavier. It would violate conservation of energy. Okay, this was sort of revitalized by myself and Raphael at Agnolo. 2015. Okay. So I can take exactly, let's take the same scenario that we just discussed in this sort of wimpless case of dark matter annihilating to a dark photon. And before, when I wrote an expression for a thermal average, I was implicitly assuming that this was lighter than this. But in general, it can be heavier, and then you have to be careful about the thermal average, which we'll describe for the momentum distribution of these. And if these collide at high enough momentum, you can make this heavier thing. So we're now on the limit. Okay, it's less than m gamma d. Okay, so you should be careful about the thermal average. So let me just tell you what that means. And then we're actually going to use a trick to avoid doing it. So I recommend actually the following paper. This paper is not about dark matter. It's a famous paper on leptogenesis, but it has a wonderful appendix, which is a good place to look up formulas involving thermal averages. And that's where I look for this. Okay. But yeah, what is it given by? Well, like when you took QFT, you're used to computing cross sections where you average over initial state and then you integrate over final state phase space. For a thermal average, you integrate over both initial and final state phase space, where the initial is whatever encodes the phase space distribution function of the particle. So that's what thermal average means. In this case, for dark matter annihilations, given by the following expression. Yeah, I'm going to be using Lorentz invariant phase space, this notation. Where that's where G is the number of degrees of freedom, state I. Okay, so Lorentz invariant phase space from you've seen in QFT class. So here I'm integrating over the initial state particles, and then it's weighted by their phase space distributions. And then, as usual, also final state phase space. Here I'll label the two photons, say 1 and 2, just explicit. Matrix element squared, and then, as usual, the delta function that encodes conservation of energy and momentum. Okay, so that's it. So it's the thing you're used to for cross section. This is the part you're not used to. When you're in equilibrium, these will just be the equilibrium phase space distribution. And it turns out there's a bunch of integrals here. You can do all except one analytically, and then there's one that you have to do numerically. And the notes I give an expression for how this looks when you get down to just one integral. It's matrix element squared times some Bessel functions that come from the thermal average times some kinematic function. So you can find it in the notes. But anyway, so this can be done relatively simply on a computer because it can be just one numerical integral. Yeah.
Are we assuming the dark photon is in equilibrium?
Yes.
Okay,
Yeah, this is in equilibrium with 0 chemical potential.
got it. So that's why there's no F term for the dark photon.
Oh, well, no, the F's are for whatever is in initial state. You can also compute the thermal average of the inverse process, which I'll label like this. So if you're going this way, then you would have F sub gamma d.
Oh,
So,
okay.
so you have the phase space of the initial state, and then you integrate over in the final state is what you're making. Yeah. Okay. So one way to analyze this forbidden case is just to be careful and compute this. But there's a trick that lets you avoid doing that, which is just to use detailed balance, because in the case where you're annihilating to something heavier, the inverse process is the usual case of annihilating to something lighter. So two of these dark photons can make dark matter, and this is heavier, and then the cross section takes the usual simple form going in this direction. So if we use detailed balance to estimate, or not estimate, to compute the phase, the thermal average. So detailed balance will just relate both directions here. And the inverse process, if I neglect order one numbers, we'll just take a simple form, alpha d squared over m gamma d squared. It's the case where you're going to something heavier, where the thermal average is going to do something more interesting. So we can, in that detailed balance, in this situation tells us that n chi equilibrium squared is equal to d chi chi. It's equal to n gamma d equilibrium squared. So it would be gamma gamma, and now I can just solve for this. So I see it's given by the simple one times a ratio of the equilibrium number densities. And that will encode the sort of magic that would come from doing this carefully. So we find well, yeah, equals this divided by this times this. The equilibrium number density should, when you're non-relativistic, just goes e to the minus m over t. So we have a ratio of e to the minus m over t's. So neglecting order one numbers, this is just e to the minus 2 delta m over t times the other direction. We're here defining delta m to be the amount that the process is forbidden by. So this just comes from the equilibrium phase space distribution Boltzmann suppression. Yeah, physically, it's just telling you that only a fraction e to the minus delta m over t of the chi particles will have enough kinetic energy to be able to make the heavier state, and then the bulk of the distribution will not be able to access the heavier state. Okay, this we can ask. So this is e to the minus delta m over t times alpha dark squared over m gamma d squared, and then. Okay, but other than this thermal average that I'm now being careful about, the rest of the WIMP story applies exactly as it did in the beginning. So this still should equal the usual 1 over t equality m Planck value. And now we can solve for the dark matter mass. Well, here it's m gamma d. But the dark matter mass has to be close to m gamma d, because if this were much heavier, like if this were 10 times heavier, the exponential would say it never ever happens. So this annihilating the heavier thing requires at most a factor of 2 splitting. So for neglecting factors of 2, I can just say this. So we have the minus delta m over t freeze out alpha d equality on Planck. So this is the thing that would be TeV if alpha is the size of weak interactions in the standard model. This exponential in general is a parameter much smaller than 1. So this really predicts dark matter mass far below TeV if this exponential is a small number, even if alpha is large. So in the prior case, I showed that you can get light masses by taking very small alpha. And this is a way of getting light masses even with large alpha because of thermal suppression in a cross section. Okay, yes.
So in general, this is a case where once you short the Boltzmann equation at the level of the phase space.
No, I'm
Even if we are in kinetic equilibrium.
if you're in kinetic equilibrium, which I'm assuming here, then you can solve the simple Boltzmann equation I wrote before, same equation from before, which
And
is
there's
just,
a number density.
yes,
So the only thing that changes is this thermal average for the.
exactly. So it's the same Boltzmann equation that I called the WIMP one. About 3h and minus COV. Minus n. So you're still solving this equation, but now this, you need to be careful what this object means. And you could do it very carefully, or this detailed balance lets you sort of figure out what it is quickly. And that was why in this step I jumped to saying it's 1/t equality on Planck. It was because it's the same Boltzmann equation. Okay. Any more questions? Okay, so we're done with 2. Okay, next, semi-annihilations. Okay, Sadia and Francesco Duramo. Jesse Taylor. Okay, yeah, indeed, before I was asked if I'm breaking rules involving symmetries. And in the WIMP case, in fact, well, so I told you in the very beginning, dark matter needs to be really long-lived, longer than the universe, longer than 10 to 17 years, if it's the case to Stammerl stuff. So typically you want this symmetry, you want it to be long-lived for a reason. So you can invoke a symmetry that makes it long-lived. And so for the WIMP case, the annihilations preserve the Z2 symmetry, where dark matter goes to minus dark matter. So I didn't even mention this because I didn't need to talk about the abundance, but you see, this preserves that, and that means that having this process doesn't spoil dark matter being stable, and it could be a consequence of this Z2. It could be stable for other reasons too. So this is just one way of making it stable. In the case of supersymmetry, you have a new Z2 symmetry of the superpartners R parity, and then if dark matter is the lightest state charge under it, then it would be stable. And more generally, if there's a new Z2 symmetry and dark matter is the lightest state charge under it, then it'll be stable. And you want whatever reactions make dark matter in your early universe to not spoil dark matter being long-lived enough. So it's a basic requirement of any model of dark matter. And this obviously violates that, but this can be consistent with a Z3. Again, I should say, so here, if it's a dark antiparticle, it would transform in the same way. So semi-annihilations are going to be compatible with instead a Z3 symmetry, where dark matter and anti-dark matter transform differently. So I can take chi goes to e to the 2 pi over 3 pi bar goes to e to the 4 pi over 3 pi bar. So in this way, chi bar, the kinetic term is okay. Yeah.
So yesterday's lectures, Jonathan was talking about how in the case of WIMPs and SUSY, when you propose these new weak scale particles, they strain your electroweak fits, and then you impose a Z2 symmetry to kind of fix that. Does a similar thing happen with Z3?
This is a very model dependent question you're asking me. In general, if these states are not charged under the weak interactions, there's no impact on electroweak fits at all.
Okay, sure.
So in supersymmetry, you're adding a lot of states with standard model quantum numbers. The Yeah, and then our priority can protect, well, not only lecture week, but various other things like flavor violation, okay, or proton decay. There are many things that can, that the new states in supersymmetry in general can cause, but this is very model dependent. So in general, if you add a bunch of particles that couple to the standard model, then beware.
Okay, yeah, I guess I was wondering about the case where these are like working in the weak interaction, but maybe that's a hard question.
Yeah, well, usually semi-annihilation models I'm aware of are usually doing it more in a hidden sector.
Okay.
Yeah, it's very model dependent.
Okay.
The Z3, this here, I'm just invoking it to protect the dark matter stability. In terms of other types of experimental bounds, it depends on how things interact with the standard model.
Thank you.
Okay. So this Z3, well, it is compatible with annihilations. Chi bar. This chi bar is Z3 neutral, but it's also compatible with semi-annihilations if I put a pi bar in the final state. So it sort of opens up a new type of process that changes dark matter number density that would be forbidden under a Z2. But you don't need to talk about the Z3, and you could apply semi-annihilations even if this is the same particle in general. It's just to point out that it's compatible with the Z3. Okay. But yeah, in a model where you have both of these, the dark matter abundance could be produced by either of these will set the chemical potential to 0 if phi has no chemical potential. So the question you need to ask is which one of these decouples later, and that'll be what sets the dark matter density we see today. So if this decouples later, you can just apply our WIMP story directly and something new to say. If this decouples later, then it's a new case. So when I say semi-annihilations, I'm going to now assume that this decouples later than this. And then we need a new Boltzmann equation to describe this type of process. I'm going to assume that the number density of chi equals the number density of chi bar, like I said, because that was assumption 3 from before. So then I can write, so now the Boltzmann equation, the left-hand side will always have the same form, but now the right-hand side will be slightly different. The first term will be the same, so I have n chi squared, sigma v chi, or again, I'm labeling it by initial state. But now the inverse process will have an n chi and an n phi. It was n phi squared in the WIMP case, so now it's something different. I'm assuming here that n phi is in equilibrium, so let me write equilibrium on that. Okay, so now it's a slightly different equation than the WIMP case. Once again, we can use detailed balance to remove one of the processes. So in this case, detailed balance tells me that n chi equilibrium squared chi equals chi equilibrium sigma v chi phi. And this, so I can solve for sigma v chi phi and plug it in to here. I arrive, let's jump up here. Again, with minus sigma v chi chi squared minus chi equilibrium. That's what you'll get if you solve this equation for the inverse process and plug in to here. And if you compare back to the WIMP case, it's almost the same thing. It's like, but before we had an n chi equilibrium squared on the right hand side, and now it's an n chi equilibrium. Okay, so how much does that matter for the big picture? Not much. It's basically the same exact story as the WIMP. Again, you're just freeze out is going to occur when n chi sigma v equals Hubble. When n chi sigma v is much faster than Hubble, setting the right-hand side to 0 is still just going to have the implication of setting n chi equal to n chi dq. So the different form of the right-hand side really doesn't matter much. It would just maybe like change slightly the curvature at the point where it's, so if you're getting the shape right, it would depend on that, but it's in terms of the gross picture, it doesn't really matter. And then the scales will be the same. So the back of the envelope estimate from before are exactly applied because that only relied on the freeze out condition, which is the same. So this has to be the usual weak scale value. But now it's this type of process. But it looks different, it's different symmetry, so slightly different Boltzmann equation, but the bottom line ends up being very similar from the perspective of the dark matter number density. Okay, any question about semi? Yeah.
So would that mean that we like weak scale masses and couplings?
If the couplings are the size of weak interaction, then we like weak scale masses.
Okay.
The same applied, again, if it's like, if this is some alpha squared over m squared, then this could be much smaller than the weak interactions, and then the mass scale would be much smaller. But yeah, indeed, it's compatible with weak scale and weak couplings, and that's nice experimentally.
So the only difference between this and like wind-like models is there might be more freedom or
Yeah, well, it's different. It can be very important in the sense of the phenomenology is going to now depend totally on how you couple it to standard model, and the phenomenology can be dramatically different actually, like, because if I rotate this diagram, then I get something I can look for in direct detection. So in general, especially if these can be like nucleons, then you have this type of thing in direct detection. Whereas in this case, if I rotate it, I don't get something I see in direct detection. So these semi-annihilation models can evade direct detection. And now if I rotate it, well, then what is kind of you have something like this now, and that's not direct detection.
but this assumes that the plus process is completely forbidden and not just like
yeah, absolutely. Yeah, indeed. So if they're both present in similar size, then it's sort of similar to WIMP, but because it allows this to now be much smaller, it can in general point to smaller direct detection. Thank you. Yeah. In general, since my mandate is production, I'm not going to explicitly say all the phenomenological implications, but every one of these mechanisms can have really big phenomenological applications. So please ask me if you want to know, or when you hear phenomenology talks later in the school, then think back about these models and then ask me what it means. It's too much for me to connect it all without 10 lectures. Okay. Yeah.
Maybe a more vague question, but how do you work with this and then couple it to a standard model particle? Like, how does that work?
Yeah, the easiest is if it's not a standard model particle, but yeah, this could be a standard model particle without a symmetry, I guess. So I could make this a Higgs and then use a higher dimension operator with I have two Higgses and put a Higgs valve, for example.
Okay, but
Yeah, so still there's a lot of possibilities is the sort of short answer.
you can tune the observable parameter as you want, like models like this, or
Yeah, basically every one of these things, there are many ways to couple it to standard model, or could not be coupled to standard model.
okay.
Yeah, which makes it hard for me to give a general answer that's not lying.
Okay.
But it is a good question. It just ends up depending a lot on the details. Yeah.
Usually in the literature, we can use some extension of the thermal perfection, right?
We can use what?
We can use some extension of the
Oh.
simulation. Does it have some implication on the final result?
Yeah, good. Thank you. I didn't mention this technical issue, but for sort of a vanilla allowed process, for the initial state is to have in the final state, you can expand in temperature. And the type of thing I've been writing down is what's called S wave, where it's 0th order in temperature. And you get something like alpha squared over m squared. Some types of processes are P wave, and that means that the first term will actually go like temperature squared. And then for the freeze out, it actually doesn't matter much because the temperature is sort of near the mass. but it can matter a lot for indirect detection in the universe today, where the velocities are much smaller than the speed of light. So it doesn't matter much for anything I'm saying. It matters a real lot for indirect detection and will be, I'm sure, a big deal in future lectures. Yeah, and for this forbidden case, it's now exponential in t, so it's even like more suppressed, much more suppressed even than p wave. Yeah. So S wave is t to 0, p wave would be t squared, forbidden, t minus m over t. And then in the universe today, t is very small, so this is extremely important for indirect detection. Okay. Any more questions? Okay. Next in the menu is co-annihilations. Which also goes back to this awesome Grice-Seckle paper. And in fact, this is the thing that Grice-Seckle paper is most famous for, because co-annihilations occur in supersymmetry, and anything that happens in supersymmetry has been studied a whole lot. Before any of you were born, though. Yeah, so again. Okay, and the sort of framework here is consider, say, within the realm of a Z2 symmetry, a tower of Z2 odd states. Where chi1 is just the lightest, and then we sort of number them by increasing mass. In the case of supersymmetry, these could be superpartners, but more generally, if I have a Z2, I could assemble the Z2 odd states. And in general, there will be decays down this tower at late times in the universe. So just the lightest state would be the dark matter that we see today. But the existence of this tower plays a role in the freeze-out calculation, because in general, you should consider all processes with sort of arbitrary index on the initial state. So you could have chi1, chi1, or chi1, chi2, or even things that don't involve chi1 at all, like just higher states in the tower could be annihilating. So in general, you need to include all of these annihilations as playing a role in the early universe. And this is in general described by n coupled Boltzmann equations. Where you can write down a Boltzmann equation for each state in the tower. Yeah.
Are these different mass states of the same particle?
No, different particles. So like this could, in the Susie case, this is like the lightest neutrino, and this could be a squark and a lepton or whatever. Just the lightest one will be the dark matter, and then the only assumption is they're all odd under whatever symmetry, Z2 symmetry. Okay. Now, so Grice and Seckle figured out a very smart trick for avoiding solving n equations, which wouldn't be fun, which is to assume chemical equilibrium amongst the tower. So assume that there's rapid exchange diagrams. Change chi I to chi j. This could take the form of a decay or a 2-to-2 scattering. So if either of these are fast compared to Hubble, they would keep the different states in the tower in chemical equilibrium with each other. And that allows you, that will set their chemical potentials equal. So set mu I equal mu j. And that actually lets you remove n-1 of these equations just by these constraints. And then you only have to solve one equation that describes the total number density of the tower. So that was a very smart observation that Grice and Seckle made for studying this system. Yeah, this is an assumption. If this breaks down, then this approach will fail. But it often holds. And then yeah, this relationship amongst chemical potentials implies that if I look at some ratio of states in the tower, it's given by the ratio of them in equilibrium. So these relations will let you move n-1 equations and then just write one equation. And it remarkably, yeah, if I define the total number density in the tower, I can write a Boltzmann equation for that object, and it turns out to be exactly the same as the Boltzmann equation for the WIMP. Where this is defined to be the sum in equilibrium now. If you intelligently define an effective annihilation rate, where you sum over all possible annihilations weighted by equilibrium number densities. So here you're summing over everything in the tower.
Checking something.
Yeah, okay. So by defining this, and you see things that involve heavier states will be exponentially suppressed by these weights because their ends will be smaller, but their cross sections could be bigger. And you can have cases where the sum is actually dominated by processes that don't involve the dark matter at all. So that's very important for, say, mapping onto indirect detection or something. Because it's the same equation now, the sum should have the usual weak scale size. So this should be the usual 1/2 equality and Planck, but because now the sum can be dominated by states that are not the dark matter, you can sort of evade indirect detection, because in the universe today, you would just be seeing annihilations of the lightest state, but the relative density could actually be produced by annihilations of the heavier states. So it seems like just a technical complication. I take the regular WIMP and add indices, but actually it's really important for mapping onto signals. Okay. Any questions about this? Yes.
Factor of 2 or 7.
Oh boy. Yeah, that's a good question. I might have a factor of 2. I don't think I have a factor of 2, but I'm not sure. Yeah, I'm not.
No, but here I'm trying to do better than that. I don't think there's a factor of 2.
I think you're supposed to count both ways, like the 1, 2 and the 2, 1, but I'd have to double check. Okay.
So I have a question.
Yeah.
I don't understand, what is a tower of states?
Oh, I just mean that there are multiple particles that are charged under the Z2.
Okay.
And I'm ordering them by masses, so I call it a tower to sound cool.
Okay.
Okay.
I have one more left here in okay, which I can totally do in 5 minutes.
So we're done with co-annihilations. Let's do co-scattering. Okay, which is related to co-annihilations. And basically, co-scattering, you could think of in the framework of co-annihilations as when this assumption of exchange breaks down. Okay. This also with myself and Raffaele. Okay. So here I'll have two states, chi and psi, that are Z2 odd. So we could sort of consider like a tower of two. Then the assumption is that this is some particle in the bath, that this is what's going to produce the amount of dark matter. And this is another Z2 odd state that has its own interactions that set it to be in equilibrium, which could be, for example, rapid annihilations of psi, but it's not going to matter what it is. But yeah, so for example, this might be happening rapidly. And as long as this is happening very rapidly, you don't have to include it in the Boltzmann equation. You can just put this to the equilibrium value. So this diagram sets their chemical potentials to be equal. And then as long as his chemical potential is zero, then it would set Guy's chemical potential to zero. So now the Boltzmann equation, you can probably guess. Here I'll jump right to what you get after using detailed balance. Okay, and this, yeah, sorry, so this is an equilibrium. This is an equilibrium, so this is the only unknown. So you have n chi and phi equilibrium minus n chi equilibrium, phi equilibrium. And the difference here is on all the other cases, we had sort of n chi squared or n chi I, n chi j in the co-annihilation case. But now you have something else appearing. And that's a very important difference because it changes the freeze out to now depend on the phi number density. So now the freeze out condition is n phi equilibrium. So it equals Hubble. And then this is exponentially different in general than n chi when they're non-relativistic. So we're going to an exponentially different cross section than the weak case, than the WIMP case. Yeah. Yes. Yeah. No. This will be the last case. Okay, so the relic density will be the usual m chi over s to equality, but now n chi is actually not determined by this, and phi is. So this I can write sort of as the ratio n chi equilibrium and phi equilibrium times n phi solving for n phi over sigma b s equality, and this plugging in the t cubed t squared over m Planck estimates will e to the minus so fine over freeze out over the usual equality and Planck sigma b. So you have this new exponential that enters the relic density, which changes the size the cross section should have by an exponential amount. They could actually be, depending on parameters, of much larger, much smaller than one. So this needs very different coupling size than the WIMP case. Yeah, so definitely matching abundance. Sigma b is e to the minus phi over t freeze out t equality on Planck. Yeah, and this can be exponentially smaller than say the WIMP size. So you can have, if you take it, if phi is lighter, then this number density is exponentially larger than chi, and that allows for the cross section to be exponentially smaller than the WIMP. Yeah.
Right, I don't understand why in the Boltzmann equation size not involved. I don't see any number density.
Oh, yeah, I use detailed balance to remove,
Okay.
yeah, I skipped to the, but yeah, what you can do is you write, this direction. And then it's n chi times n phi, and then you have this direction and psi times n phi. But then detailed balance relates those two, and then the n psi drops out. So I skipped that stuff.
Okay.
But it's a good exercise to make sure you understand detailed balance, is to figure out how to get to here. Okay. So that is it for two symmetric thermal relates. Yeah.
What does the thermal freeze out temperature? What does sets this temperature in this case where you have the dependence on the n phi?
The temperature, simply to match what we observe, has to be given by the universal form that I wrote before, this sort of 10 to x of 10 to 30.
Okay, so also in this case.
Yeah, in every case I talked about today, that has to apply because the same yield cartoon is always applying. So I'm always doing this, and I'm in equilibrium, and then I have the observed value. So this x freeze out is given by the universal form I described before. That's to match observation. Now you have to ask what cross section should I have to achieve that, and then that indeed depends on parameters and can be determined by solving the freeze out condition in each case.
Other questions? Yeah, when you speak about the dark photons or they need to like disappear quickly after they produce or something like this because they or do they leave signature that we can observe?
Yeah. Well, in the case where I was studying models where I'm annihilating into them, I was assuming, at least for my analysis, I was assuming that they have zero chemical potential and are in kinetic equilibrium during freeze out. The simple way to enforce that is if there's a kinetic mixing between our photon and the dark photon. In the Lagrangian, you have epsilon f mu nu, say f dark mu nu. So it's like the kinetic term of the photon, but now you mix the two field strengths. If you have this, and if the dark photon's massive, you can remove this mixing by redefining the massless field, and then this generates a coupling of the dark photon to the electromagnetic current. And this is now proportional to the electric E times this epsilon parameter, which could be much smaller than 1. And then as long as this decay is faster than Hubble, then that assumption would be manifest. And then indeed, they would then decay very rapidly in the early universe into the standard model bath. So that would be the simplest way of achieving that, which wouldn't have a direct signal cosmologically. But if this coupling is present, then there are many experiments you can use now to look for this, like fixed target experiments and colliders.
You can always bother Josh during the coffee break. All right, thanks Josh for a great presentation.